I hope I'm audible.
Good evening, ma'am.
Good evening. Okay, so let's start. Today we'll be starting with some problems on differential calculus. Start with question number 1. Let f be a function from a domain U to R, that this U can be subset of any Rn. F is said to be radial. We know that for radial functions, the value remains same on a circle, or we can say that whenever the modulus, the norm in the domain is same, the function is constant. Or technically, if we can write if fx is equal to fy whenever norm x is equal to norm y. And by norm here, we mean the Euclidean norm. Okay. So consider a function f from Rn minus 0 to R be a differentiable radial function, and g is a function that is defined on R plus to R is such that g uh, f at any point x is equal to g at norm x. Obviously norm x is a positive entity, so g is well defined on norm x. Then we need to show that this function g is differentiable. So that g is differentiable with g dash and there is a relation between the derivative of g and the gradient of f, and gradient of f at any point x is given by g dash r by r times x, where this r is nothing but norm x. Conversely, we have, okay, we'll write that converse part as second part of the problem. Okay, so let's start with the differentiability of g. Directly, we can use the differentiability of f to show that this function g will be differentiable. So we have limit h tending to 0, g r plus h, let r belonging to r plus be arbitrary. So we are checking its differentiability at point r. Then limit h tending to 0, gr plus h minus gr by h. This can be written as limit t tending to 0, so if I mark this as 1, this is f u plus tv minus fu by h. This is by first, where this u is such that norm u is equal to r. And obviously, we can always find some t such that some v such that this norm of u plus tv can be taken as close as we want to the norm of u, which is r. So I can take this to be r plus h. So basically, we are taking this t tending to 0. Eventually, this norm will converge to norm u. Similarly, here, when we take h tending to 0, so instead of t, here we can take h. H. So now since f is differentiable, we know that this limit exists, um, which is basically the directional derivative of f in the direction of v at point u. Now since f is differentiable, dvf u exists for any v. This implies limit h tending to 0, gr plus h minus gr by h exists, and hence this function g is differentiable at r. Therefore, our function g is differentiable because we have taken arbitrary r and r plus. So the main idea was that the function f is differentiable and hence it all of its directional derivatives exist. Therefore, the function g is also differentiable. Next, we need to show that if g is differentiable, then gradient of f can be written in the form of derivative of g. So can you tell me how do we evaluate this gradient? So what is basically gradient?
Gradient.
So is it a vector or a scalar quantity?
Gradient is a vector quantity, no?
Exactly, it is a vector. And how are its components defined?
Del f by del x1, del f
Corresponding
by del
partial
x.
derivatives,
Yes.
something like this. So what do we want? We need to show that this gradient at any point x is actually equal to g dash r by r dot x. So here this is again a vector where the terms are something of the form this. We want our gradient to be of this form. So that means we need to evaluate the partial derivatives of f. Okay. Now we have fx is equal to g norm x. So we can use the chain rule to find the partial derivative. This implies del f by del x I. This is equal to g dash norm x del by del x I of norm x, and the norm is the Euclidean norm, so I'll write it explicitly. This is under root x1 square, x2 square, so on up to xn square. So this is g dash norm x. So if you differentiate, you'll get 1 by 2 root So n square is n square times 2. So this is 2xi. So this one get cancelled out. So since this denominator is again norm x, xi. So the vector gradient f at x, this is equal to del f by del x1 x, so on up to del f by del xn at point x. And we know that each of the component is of the form g dash. Now if I replace norm x by r, so this will be g dash r by r x1, so on up to g dash r by r xn. That's what we want. So we can take this g dash r by r outside and we'll be left with x. Gradient fx. I hope this is clear how we proved the differentiability of g and the gradient of f in terms of g. So radial functions are actually very good functions because they are eventually taking the uh, higher dimensional function whenever we have our function is a vector valued, suppose, and if we know that the function is radial, so eventually it is depending on a one variable function. So basically we can find the properties of f using this function g. G is a one variable function, real valued function. So such radial functions turns out to be very helpful for us in many scenarios. So let's see the converse part. Uh, you want me to explain the first part from beginning? So basically we started with showing that this function g is differentiable. We need to show that this function g is differentiable. G is nothing but a real valued function. When we have a radial function, we know that on a circle, the circle, which is basically norm x is equal to some constant, on this circle, we know that the value of the function remains same. So we define a new function g, which is depending, whose domain is just r plus, in such a way that f of x is equal to g at norm x. Now norm x is a real positive real number. So clearly we can find any x such that norm x is equal to some alpha for any alpha in R. So yes, this g is well defined. Next, we need to show that this function g is differentiable and such an equality holds. So in order to prove the differentiability, we start with the basic definition. We prove that this limit exists, and the way g and f are related to each other, from there we get the second equation. And then by differentiability of f, since we are given that f is a differentiable radial function, so all of its directional derivatives exist, therefore this derivative of g exists as well. So I hope this is clear.
G of r plus h becomes f of u plus h v. How?
So see, r is a real number, so clearly I can find any vector u such that its norm is equal to r. What do we mean by norm u equals to r in Euclidean plane? It is lying on the circle.
R is positive, isn't it?
Yeah, norm is also always positive.
Yeah.
Any point, any vector lying on this circle, suppose this radius is r, any vector lying on this circle will have its norm equals to r. So I can always find such a u. And then we are taking this u plus hv. So u plus hv basically it is somewhere around u, because h is small. If I take h small enough, so it is lying on some straight line around u. So basically, it is inside the circle. So that can its norm will be any point lying here. Its norm will be either r plus h or r minus h, because this distance is r. If a point is lying here, this is r minus h, r minus some small quantity. If it is lying here, it is r plus small quantity. This h can be positive and negative. Basically, this h is tending to 0. So that is why we can write this. Now, since norm u plus h, we can take this to be r plus h. So by this equation 1, I can replace g by f. So the main idea is that G is defined on positive real numbers, and the norm of any vector is again a positive real number. No?
Okay. Actually, we are adding HV. It means we are adding vector V, a
Yes.
small part of vector V in U.
Uh, we are actually translating it near to U. So
Okay, okay.
if we can be somewhere here also, but when we are multiplying it with very small h, we are eventually translating it to here. Okay. So yeah, the idea is the same. We need to be near U in order to see. Then again, yeah, using the differentiability.
Okay, ma'am.
Okay. So next part is something converse of this. Now suppose f is differentiable. Suppose f is a differentiable function. Function, and there exists a function. And there exists a function h defined on Rn minus 0 to r, such that gradient of fx is equal to hx times x. Then show that this function f is radial. So in order to show that a function is radial, we need to show that it remains constant on a circle. If I take any circle, the value of the function at each of the points on the circle should be same. That's the main definition of the radial functions. So here we need to show that the function f is radial. That means if there exists, if x and y are such that norm x is equal to norm y, then we should have, then we must have f at x is equal to f at y. So let's see. We'll show this by using path. So consider a continuous function, some function gamma, which is defined from close interval 0, 1 to SR, where SR, so let's start with arbitrary R positive. Let R positive be arbitrary. SR be the set of all those points X in Rn such that norm X is equal to R. So basically this is the circle. Now we consider a path So by path we mean a continuous function. Consider path. So this can be arbitrary function. All it needs to be is continuous. Even the domain can be different. Continuous. And the range is SR. So we will show, uh, okay, let's see. Now, f composed with gamma, this is a function from 0 comma 1. Gamma is in converges, range of gamma is SR. Then f range of f is R. Then d by dt of f of gamma t. This is equal to d by dt of, so, so by chain rule, this will be equal to gradient of f at gamma t times gamma prime t. This comes by chain rule. So this is by chain rule. Now we are given that this gradient f is equal to hx times x. So this is hx, sorry, gamma t, no? Because gradient of f at gamma t. So this is h at gamma t times gamma t times gamma dash t. Now gamma t is just a function defined on, it is a continuous function. So we claim that gamma t times gamma dash t is 0 for every t. Close interval 0 to 1. Now gamma t dot gamma t, because gamma t is a vector in SR, so this is a dot product. This is equal to norm gamma t square. Now can you tell me what will be norm gamma t? Our
R.
function, yes, this is R. Because our function gamma is defined from 0 comma 1, from interval 0 1 to SR. So gamma t lies in SR and SR contains all the vectors with norm R. So this is equal to R square. This is happening for every t in 0 to 1. Now let's differentiate both sides. This implies d by dt of gamma t dot gamma t. This is equal to 0 because this is constant. And by product rule for the dot product, this is equal to gamma t times gamma dash t plus gamma dash t times gamma t. So this is equal to 0. That is basically 2 times gamma t gamma dash t. This is equal to 0. That's what we want. Gamma t times gamma dash t. This is equal to 0. Now this implies d by dt of f of gamma t is equal to h gamma t times gamma t gamma dash t. This is equal to 0. Now this gamma was an arbitrary continuous map from closed interval 0 1 to SR. We can construct it in any way. So eventually we can see that whole SR can be considered to be the range. In that case, we get that d by dt of f at we can write this x is equal to 0 for every x in SR. Now, since gamma is an arbitrary path in SR. Now, SR is a connected set and the derivative is coming out to be 0 on a connected set. That means the function is constant on that domain. That this implies f z, or we can write fx is equal to some c for every x in SR, because SR is a connected set and derivative of f on SR, this is equal to c. So instead it will be, yeah. Therefore, f is constant on SR. Now, since SR was an arbitrary sphere, so the function is radial. Yeah, since R positive is arbitrary, we get f is a radial function. In order to show that the function is radial, we started with a path, a path on SR on the circle or the sphere, and using the given condition on the gradient, we have shown that the function remains constant on the circle, and hence the function is radial. I hope this
Ma'am,
is clear.
here
Hmm?
the gradient of fx that is defined to be hx into x. This is a dot product or simple product.
See, hx is a real number because the range space of h is in R. So hx is a real number and x is a vector. So we are just
Okay.
scalar multiply. It is kind of scalar multiplication.
Yeah.
So I hope this is clear.
Then here h of gamma t into gamma dash t,
Hmm.
and then dot of gamma dash t. Gamma t into gamma t and dot of
This is
gamma dash t is
this is
0.
not the dot product, because gamma is just a real valued function defined on real the space, the domain is also real, no? So this is just real valued function with one variable. So this is simple multiplication, gamma t times gamma dash t. No, gamma t is a vector in SR. Yes,
Actually, gradient of f
this is
of
a
gamma
dot
t
product.
dot product. Then here gamma t and gamma dash t, we prove that their dot product is 0.
Hmm.
Then how that h of gamma t into gamma dash t dot of gamma dash t becomes 0?
You're asking here.
Yes, ma'am.
Is this fine that gamma t times gamma dash t will be 0?
Yes, yes.
So now h gamma t, our h, this is a function. This is basically composition. H gamma, domain of gamma is close interval 0 to 1. So this is a real valued function, na? H gamma t. This is a real number. This is multiplied by
Mhm.
some. I think this will be a linear map because gamma dash t will be a linear map. So by this zero we mean the zero linear map. Hmm. And we are multiplying it with h gamma t, where h gamma t is just a real valued function. H of gamma, this is just a composition map. Gamma is a function from close interval 0, 1 to r. Sorry, close interval 0, 1 to SR. So the domain will be close interval 0, 1. And the range will be the range of H. The range of H is R. So this is just a real valued function. So this is just multiplication. And this is scalar dot product. This will be a vector. And this will be a linear map, which is again a vector. We can write a linear map as a vector. We can write linear map when f t is from Rn to Rm, we can write it to be a matrix.
Yes, ma'am.
And when we have this just R, in that case, that matrix will be a vector. This gamma t
Yeah.
will be something of that form. Sorry, gamma dash t, because gamma is basically R from R to Rn, something of this form, some subset of Rn. And in this case, gamma dash will be a linear map from R to Rn. So basically, this is a vector. And gamma t is also a vector. So this is a dot product and this is just scalar multiplication because this is a real number. So here we have dot product and this is not dot product. So I'll write it properly. This is H gamma t times gamma t dot gamma dash t. Okay, is it clear now?
Mm. Actually,
Hmm?
we change the association here. Uh, H of gamma t is multiplied with gamma t first, na, and then we will take the dot product with gamma dash t.
Yeah, we can take this H gamma t outside also.
Ocha, okay, it is constant. So,
It is kind of scalar multiplication. Na? Here we are doing dot product. So eventually this
yes,
can be
ma'am.
taken out. And this since this is a zero, this will be scalar because after dot product we get zero. So this is zero. Yeah, this is zero real number and it is multiplied by h gamma t. Okay. So yeah, the derivatives in higher orders are a bit complicated. So I hope this
Mhm.
is clear now. This is
Yes,
dot
ma'am.
product and eventually we get a real number which is multiplied by h gamma t. H gamma t is again a real valued function. Okay, let's move to next question. Suppose the directional derivative in the direction of b of f at point A exists. What is d minus vf? Construct a function. Construct a function f from Rn to R such that for some vector v in Rn, dv fx is strictly positive for every x in R. So since dvfa exists, therefore, since the directional derivative of f in the direction of v at point A exists, this implies limit h tending to 0 f a plus hv, sorry, h minus f of a by h exists. Now using this limit, we'll find the directional derivative in the direction of minus v. So now d minus vfa, this is nothing but limit h tending to 0 f a minus hv minus f of a by h. So just a little bit of calculations. This is limit h tending to 0. So I can multiply and divide by minus 1. So I can take this as f plus minus hv minus f of a for minus h. So I can write it as minus limit h tending to 0. So instead of h, I can write it to be k, where k is minus h, a plus kv minus f of a by h. Sorry, k. And k is minus h. Obviously, whenever h is going to 0, k is going to 0 as well. And now this is the definition of dvfa. So this is minus the directional derivative of f in the direction of v at point A. So it is just the negation, negative of dvfa. Now we need to construct a function such that dvfx is positive for every x. So can you give me some example? We need to find f from R into R such that for some v, dvfx is strictly positive, and this is happening for every x in R.
Ma'am, f of x, maybe we can take x to the power 4, comma y to the power 4, and z to the power 4.
Okay, you are taking in three variable. So
Yes,
this is
ma'am.
f, x, y, z. So what v should I take so that in that direction the derivative is positive?
Ma'am, I am stuck here.
So it will be better if we go to one variable to look for idea. So in one variable, can you find some function whose derivative is always positive? Easiest function whose derivative is always positive.
Ma'am, if we take f of x to be x identity function,
Yeah,
then in
let's
the
okay.
direction of each coordinate,
So we know that for if we take fx equals to x, in that case f dash x is equal to 1, which is always positive. So if we are working in Rn, suppose x is a vector xn, I take it to be equal to x1 plus x2 and so on up to xn. Now if I take v to be 1, 0, 0, so we know that the directional derivative in the direction of v is the partial derivative with respect to first variable, because this is just 1, 0, 0. No? So at any point x, this is equal to del by del x1 of f at x. Now here, from here, we know that the partial derivative will be 1, which is always positive for every x. So that's how we take the idea from one variable and move to multivariable. Similarly, you can take this to be x cube, x1 cube, x2 cube, xn cube, because we know that the derivative of x cube is 3x square, which is always positive. And we know that if we take v to be, we can take v to be any of any ei. So it could be 0, 1, 0, 0. So in that the directional derivative in that direction means the partial derivative with respect to the second variable. So yeah, that's how you can construct examples. Okay, let's move to next question. Suppose f is a function.
We are taking linear function there.
Yeah, because it's easier, na? We can easily evaluate the partial derivative.
Yes.
That's why we are taking the sum. Suppose f from bxr. So bxr is a ball around x with radius r to r is differentiable at x, and assume that fx is greater than equal to fy for every y in bxr. What is dfx? So what can you say about the derivative? So any idea? Start with the idea we have in one variable. So since fx is greater than equal to fy for every y in the ball, that means x is a local maximum.
Maximum.
Exactly, because there exists a neighborhood around x where the value is lesser than fx. So
So the derivative will be 0, isn't it?
yes, it should be ideally 0. So yeah, let's see how we can prove this. Not that big tough proof. So we are given that the function is differentiable at x. So we'll take use that. So we know that if f is differentiable at x, then the derivative is given by, the derivative is again a linear map, and at any point y it is given by limit t tending to 0 f x plus ty minus fx by t. Now we need to prove that this is equal to 0. Now let's see this fx plus ty minus fx. So can you tell me its sign, whether this will be positive, negative, or 0, or depend on t?
It it will be always negative because x is maximum.
Because x is maximum in the neighborhood. So whatever the value of t is, t can be positive, negative. Always fx will be greater than fx plus ty when t is near to 0. So this is always negative for
Ma'am,
every.
derivative here, derivative will be a linear map, no? So
Yes,
how
yes. Because
how
we
this
are,
definition of derivative will give a matrix?
so you want to look back at the definition. So the way we define for several variable functions. Huh? So
Yes.
yeah, let me recall. If we have a function f defined on U be some subset of R and to R, then we say that f is differentiable
It X belongs to U.
at some x belonging to U
There
if
exists a
there
linear map.
exists a linear map. There exists a linear map.
DFX.
Suppose. Yeah. Let's write that
DFX
dfx such that
from
fx
Rn
plus
to R.
h. Okay. Now this df, the domain of df is same as that of f. So this will be institution
Rn,
write it u.
Rn to R.
Yes. R into R. Basically, the domain and codomain are same as that of f,
Oh,
such
oh.
that and dfx such that f of
Limit.
x plus h is equal to
mm,
fx plus L, or instead we can write dfx at
Times H.
h plus e of h, where this e is basically the error function.
EH tends to 0. EH by norm H tends to 0. H tends to 0.
So basically, at any point in one variable, we used to find the derivative at one point used to be a real number, but here derivative at one point x is a linear map whose domain is same as that of the function domain and codomain. So here our function f is defined on bxr, which is a subset of Rn. So our df x is a linear map. So it is defined on bxr. So this y is in bxr. Okay. So yeah, by the given condition, we know that fx plus ty minus fx is always negative. Now we need to check the sign of the whole term. Then
And
fx
domain of
plus
dfx will
hmm,
be U or Rn whole?
u the domain of
U.
the domain of the function, because outside that we don't know na. See, in the definition we need to put this y inside of f. We need to
In
find value of
dfx takes H input. No, H is from U or H is from Rn.
from what h, this h.
Yes, H is from Rn or U.
Yeah, u. H is basically a small term. We generally take it from a ball near zero. So eventually we need this x plus h to be in u. So we need, suppose we have x here, we want, and our u is something here, we want our h to be such that x plus h in any direction, this x plus h should lie inside the ball. So if a function h we are adding here, its norm should be smaller enough so that we remain inside the ball, inside the space set u. So that is why we take h to be in small ball around 0. That means the function, the norm of h should be near to 0. That's our aim. We want to take this h to be small enough so that x plus h always remains in the domain, and we can find the value of f of x plus h. And eventually we need to take this h tending to 0 in order to find the derivative. So this h always lies in a ball near 0. We say that it lies in a ball near 0 so that x plus h is in u. Because basically we need to define f. So you are saying that here we should write ball around 0.
Hmm. Actually, H is in Rn and we translate it in the ball. We're taking it small in Rn so that its translation
All we need to
x
make
plus
sure
h is
is
in
that x,
ex.
yes, x plus ty, this or x plus h, what we took in the in that definition, this should lie inside the domain of f. That's the main
Yes.
point.
Yeah.
So yes, now this is always positive. This is always negative, and if we divide it by t, now its sign will depend on t. Suppose this will be negative if our t is positive, and this will be positive because negative negative. This will be positive if t is negative. That means we have limit t tending to 0 minus fx plus ty minus fx by t. In case of negative, this is greater than equal to 0, and limit t tending to 0 plus fx plus ty minus fx by t, this is less than equal to 0. So eventually from here we get 0 less than equal to limit t tending to 0 minus x plus ty minus fx by t. Now since f is differentiable, so this limit exists. So this must be equal to limit t tending to 0 plus fx plus ty minus fx by t, and which is less than equal to 0. Now this is happening because f is differentiable. This gives us limit t tending to 0 fx plus ty minus fx by t. This is equal to 0. That is the derivative of f x at y. This is equal to 0 for every y wherever the function is defined. Or we write df is 0. df at this point, at point x, is 0 map. I hope this is clear.
Ma'am, how that limit t tends to minus 0 minus x plus ty minus fx by t is greater than equal to 0?
See, the numerator is always negative. When we
Oh,
are taking t from
interesting.
negative side, so the numerator and denominator negative negative turns out to be positive. Similarly for 0 plus.
Okay, thank you.
Okay, so yeah, let's move to next problem. Next, we'll be using the method of Lagrange multiplier. Number 4. Let S be a subset of U be the level hypersurface. So, do you know what do we mean by level hypersurface? Okay. Level hypersurface. Surface of the function g from U to R. That means S is the set of all those points where g takes a constant value. Let f from U to R be a C1 smooth function, so by C1 smooth we mean all partial derivatives of f exist and are continuous. Suppose P belonging to S is a global, instead we should write the global maximum of F on S. Show that we can find a real number lambda such that gradient of f at p is equal to lambda times gradient of g at p. So we are given that S is a level hypersurface corresponding to the function g. And then there exists a point P in S, which is the global maximum of F restricted to S. So since P belongs to S, that means S is G inverse C. That means G of P is C. And P is global maximum of F on S. That means P solves the problem, the constrained maximization problem, maximize function fx subject to, if I take gx minus c to be equal to 0. We know we can solve such a constrained maximization problem using the method of Lagrange multiplier. This is called constrained maximization, or instead we write it as constraint optimization problem. Optimization problem. So now we define a function f, sorry, let's define it n x comma lambda. So we have another variable lambda as well. We define it to be equal to fx plus lambda times gx. Then we know that solving 1 is equivalent to finding global maximum global maximum of L. Now we know that the problem 1 has a solution given by P. Since first is solved by P, and earlier we have seen that the derivative of the global maximum is 0. That means all of its partial derivatives will be 0 as well. This implies del by del lambda f at f p comma lambda is equal to 0, and del by del xi of f at p comma lambda is equal to 0 for every I 1, 2 to n. We take this U to be subset of R. Okay. So yeah, sorry, not F, this is L, the new function. So from here, we can see that if we differentiate L with respect to lambda, we get, oh sorry, this should be Gx minus C. We get Gp minus C equals to 0. That means Gp is equal to C. That is P lie on S. That's true. You know that P is an element in S. And from here, we get del by del xi of f at P plus lambda. So instead of plus, we can, okay, let it be Gp. This is equal to, sorry, del by del xi P for every I 1, 2 to n. So I can replace this by lambda bar, lambda bar. This implies del by del xi of f at point P is equal to minus lambda bar del by del xi of G at point P. Taking lambda to be minus lambda bar, we get del by del xi fp. This is equal to minus, sorry, x is equal to lambda del by del xi G. Gp. Yeah, from here we get gradient f at point P is equal to this, and this is happening for every I 1, 2 to n lambda gradient G. That's what we need to prove. So yeah, here this lambda bar is a variable. It is treated as a variable, and since the problem has a solution, then it can be solved by some lambda p comma lambda bar. Yeah. So this lambda bar is fixed. We can find such a lambda bar. So I hope this is fine.
I don't understand.
Which part?
I don't know what is constant optimization problem.
Constrained optimization problem. Constrained optimization problem is basically you are optimizing a function with a constraint. So we need to find maximum of fx. We need to find a x, some point x, which is maximizing f, or and also satisfying this condition. So this x should maximize f as well as it should satisfy the condition that gx is equal to c. So you can go through the method of Lagrange multipliers using, so the main idea is to consider a new function lx lambda bar, and then we try to find the global maximum, global minimum, because constraint we do not have direct way to solve, but in one variable we know that we can easily find global maximum of a function of this form. All we need to do is differentiate with respect to sorry in finite number of variables. We need to partially differentiate. Then we'll get the critical points, and using the similar analysis of multivariable, we can find the maximum minimum. So yeah, you can go through the method of Lagrange multiplier. You can easily Google it up. It's on Wikipedia also. That's how we prove it. So the main thing is that solving equation first is equivalent to finding the global maximum, or here we can, this similar method is used for minimum also. So solving problem one is equivalent to finding global maximum minimum of the new function that has a new variable. So if we had only one variable, now we are in two variable. That's how we solve the constraint problems. Is it fine?
Okay, ma'am. I need to see the Lagrange multiplier. Okay.
I think you must have done it sometimes in graduation, because it is quite calculative, nothing big sort of things, just calculations. Okay, let's move to next. Let's move to next question number 5. Suppose f is a function defined on the ball bxr, real valued function, is such that its derivative, such that the derivative is the zero linear function at all points. At each point, the derivative is the zero linear map. What can you say about the function? So what can you say?
A function is constant
Yes, because our
on
domain,
BX
is connected set,
connected, yes.
and the derivative is linear. So it seems that the function should be constant. So let's see how to show that this is constant. So for that, we will be using the mean value
Polygonal
theorem.
lines. Okay.
What lines?
Polygonal lines. We can connect any 2 points by polygonal lines and then you
Yeah.
can prove.
Hmm. So we'll start with straight line only. That will be
Oh,
helpful.
yes. Oh, yeah, because it is a ball.
Hmm. We define a function gt as f of 1 minus t. So let's start with some y and y plus h. Let y belongs to bxr and h. Yeah, let's start with y and y plus h be two elements in the ball bxr. Then we define a function g such that g of t, this is equal to f at 1 minus t y plus t times y plus h. So basically, these points are the points on the line. So if this is bxr, this is y, this is y plus h, all these points t times y plus h plus 1 minus t times y lie on this straight line. So obviously we are inside the ball. So now g is a function whose domain is a real number, need not be whole R, it is a subset of R, and it is real valued function. So here we can apply the mean value theorem. Clearly, since f is differentiable, so this g is also differentiable and hence continuous also. Since f is differentiable, this implies g is also differentiable and continuous in its domain. So domain of G is, yeah, it's closed interval 0 to 1, no? Because we want to make this straight line for every t lying in closed interval 0 to 1. So G is differentiable in open 0 to 1, continuous in closed 0 to 1. So by mean value theorem, we have there exists some zeta lying in open interval 0 to 1 such that G1 minus G0 by 1, this is equal to G dash zeta. Now G1 is f of y plus h. That means f of y plus h minus G0 is f of y. This is equal to G dash z. Now since the derivative of f is 0, we know that 0 is equal to limit h tending to 0 f of y plus h minus f of y by norm h, which is equal to limit h tending to 0 g dash xi by norm h. Now since this limit exists, here the denominator is tending to 0 as h tends to 0. So the numerator should also be tending to 0, because if that's not the case, the limit won't exist. This implies g dash zeta should be equal to 0. That means by first, G1 should be equal to G0. First, G1 should be equal to G0. That is, Fy plus H should be equal to F of y. That means Y is constant in its neighborhood. Eventually, F is constant in the neighborhood of Y, and since Y is an arbitrary element in BXR, so eventually it is constant in whole BXR. This we can do only because we are in the connected domain. Since y belonging to BXR is arbitrary and BXR is connected, from here we get f of f is constant. So basically we started with arbitrary y and showed that it should be constant in some neighborhood of y, and since this y is an arbitrary element in BXR, so everywhere it should be the same, and hence the function is constant. Next, we will see that if all the partial derivatives of a function are bounded, then the function is continuous. Let f,
And there is also a form of mean value theorem. You can also prove that from that form also, no?
which form?
Um, if a function f is from a concept U subset of Rn to Rm,
Hmm.
and for
Here
any
they
two
want.
given points,
Hmm.
if line joining the 2 points on in
In
U,
that case, basically this xi belongs lie on the line joining the points, na?
yes,
So
yes.
it's the higher dimension version of this. Yeah, that can also be used.
Actually, these two mean value theorem are equivalent or not?
That's basically the generalization of this. So we can say that the mean value theorem that you have studied till now is a special case of that one. That is for arbitrary n dimensional space, and the special case is when n is equal to 1.
Okay. Thank
Let
you.
f from u to r be such that all the partial derivatives exists and are bounded. Bounded. Show that f is continuous. Here also we'll be using the mean value theorem. So basically, we know that f is different, f has all its partial derivative. So if I consider f1 to be a function that is defined on some subset of R to R such that f1x is nothing but f of x and rest of the terms are constant. Suppose x naught 1, x naught 2, so on x naught n be a fixed element in Rn, and then I define f1 to be a function where the first component is a variable and rest of the terms are constant. So what can we say about the differentiability and continuity of this function f1? We know that
It will be differentiable. First derivative exists. Means.
it will be differentiable because the partial derivative means differentiation with respect to the first variable, taking others to be the constant. That's what we are doing in this function f1. So since it is differentiable, it will be continuous as well. That means we can apply mean value theorem on this f1. In fact, similarly we can define fi. So that's the main idea. Let's see how we'll prove this. The idea is to apply mean value theorem on these functions fi. So we need to show that f is continuous. Let x naught equal to x naught 1, x naught 2, so on up to x naught n belonging to Rn be arbitrary. So we'll be checking the continuity at point x naught. Then,
Element of U.
okay, u. And then mod fx naught minus fx. This x is somewhere near x naught. This is f of x naught 1, x naught 2, x naught n minus f of x1, x2, so on up to xn. So I can write it to be equal to f of x naught 1, x naught 2, x naught n minus, I'll just replace the first term by x1, rest of the terms will be same. Then adding the same term. Next, I will take the same point with the difference at the second component. So the first component will be same, x1. I'll replace x naught 2 by x2 and rest of the terms will be same. X naught 3 to x naught n plus the same term. In this case, I'll take all other components same except the third term. And so on. We have f. So eventually from x naught i's to we are converting to x i's. It will be
xn minus 1.
x naught n minus f x1, x2, and so on up to xn. Yeah, x naught n minus 1, that will be term above this. So is it clear why I'm doing this? Then I'll be using the mean value theorem. So this is less than equal to mod fx naught 1, fx naught 2, x naught n minus, because rest of the terms are same. And x1, x2, x3, and so on. X1, x2, n minus x1, x2, x. So in the first term, only the first component is different. So we can apply the mean value theorem. This will be equal to, so that is basically derivative with respect to first variable of f at some point xi1 times, this will be x naught 1 minus x1. Similarly, the next term will be d2 f at some xi2 times x naught 2 minus x2, and so on up to dn of f at some xi n x naught n minus x n for some xi I, which is between x naught I and xi. This is by mean value. Now this can be, now since all the partial derivatives are bounded, I can write it to be less than equal to m times summation I from 1 to n modulus x naught I minus xi, which goes to 0 when x goes to x naught. So this can be made less than epsilon, or I can write it to be this goes to 0 as x naught, sorry, as x goes to x naught. So therefore, fx goes to fx naught as x goes to x naught. Therefore, x goes to fx naught as x goes to x naught, and hence f is continuous at x naught. So please go through this calculation part again. If you have any doubt, please let me know.
Mm, mm. D1 f of xi1 का modulus into x naught of 1 minus x1.
Hmm.
Can we in place of x naught 1 minus x1 multiplied by norm of x naught 1 x naught 2 up to x naught and minus x1 x2 x1 x
No,
naught
no,
2.
I am using the mean value theorem of one variable.
Oh, the
Because
difference in first variable. Okay.
yes, yes. This is partial derivative basically.
Okay.
So these are actually, we can consider these to be n different functions which are of one variable, the way I defined fi earlier in similar way, and then we are applying mean value theorem.
Very cleverly, we actually
Hmm.
convert n variable function to one variable function here.
Hmm. Okay, then let's move to next question.
Okay, ma'am.
7. Let f be a function from u to r, where this u is a subset of some r n, be such that d1f, that means the partial derivative with respect to first variable, d2f and d2 d1f exists and are continuous. Show that d1 d2f exists and d1 d2f at any point x, this is equal to d2 d1f for every x in u. That means the partial derivatives can be interchanged. This can be done only if we are given that the partial derivatives are continuous. When they are not continuous, in that case, we cannot do it. And we'll see one example for that as well. So let's see this one. So we need to show that this d1, d2f exists. So firstly, see how how can we evaluate this d1, d2. So suppose y1, y1 comma y2 be some point in u, and we'll evaluate the partial derivatives at that point. So d1 d2 f at y1 y2, this is equal to d1 of d2 of f at y1 y2. So d2 of f, that means this is d1 limit k tending to 0 f y1 comma y2 plus k minus f of y1 y2 by k. Next, we need to differentiate it again. So this is equal to
Only two
limit.
components.
Okay, yeah, because we are asked to find d1 d2 only, so I am taking advantage of that and doing it only for two variables, because all we need to show is that del by del x, del 2 by del x1 del x2, this is equal to del 2 by del x2 del x1. So yeah, if we prove this for just two variable function, then we are done. So that's why I'm taking
Mm.
it to be R2.
A rest of variable are considered to be constant.
Yeah, that can be considered constant. So if we prove it for just for R2, then also we are done. Otherwise, you can try it yourself. You need to increase the number of components here. And yeah, that will not affect the proof.
Mm.
So limit h tending to 0, limit k tending to 0. So wherever we have y, we need to replace it by y1 should be replaced by y1 plus h. Y2 plus k minus f of y1 plus h y2 by k minus, so here it should be as it is, limit k tending to 0 f y1 y2 plus k minus f y1 y2 by k on h. So this is how, if this limit exists, then we can say that d1 d2 exists. So let me take this limit k tending to 0 outside and simplify this. So this will be limit h comma k tending to 0 f y1 plus h y2 plus k minus f y1 plus h y2 minus f y1 y2 plus k plus f y1 y2 upon hk. So we need to show that this limit exists. For this again, we'll convert uh, to one variable problem. So let's see how. Let's mark this as 1. Define a function gt to be f of y1 plus h comma t minus f of y1 comma t. Now, since d2 exists, that means f is differentiable with respect to its second variable. That means which is the main variable of the function g. Therefore, g is differentiable as well as continuous. Hence, we can apply mean value theorem on g. Since d2f exists, this implies we can apply mean value theorem on g. This implies That's right. There exists some zeta 2. I'm taking this zeta 2 because we are working in the second component. Zeta 2 between y2 and y2 plus k. So such that g of y2 plus k minus g of y2, this is equal to g dash zeta 2 times k. Now g dash at point zeta 2 is basically, this is equal to d2 of f at y1 plus h comma zeta 2 minus d2 of f at y1 comma zeta 2 times k. Now, by linearity of the different of the derivative operator, I can write it as that d2 of f y1 plus h comma zeta 2 minus f y1 comma zeta 2. Now again, we can apply the mean value theorem on the function f1. Now, if we define f1 from some interval I in R to R, f of t, f1 of t is just f t comma
Ma'am, here
zeta.
derivative of g gives the second partial derivative of f. Isn't it?
This is not second partial derivative. This is the partial derivative with respect to the second variable,
Oh, yes, yes, yes.
because here we are differentiating with the with respect to second variable.
Mhm.
So this now in this case we are defining f1, which has the first component as the variable. So now since d1f exists, we can apply mean value theorem on f1. By mean value theorem, there exists some zeta 1. I'm taking zeta 1 this time because I am in the first component. Zeta 1, which lies between y1 and y1 plus h, such that f1 y1 plus h minus f1 at y1 is equal to f1 dash zeta 1 times h. So which is basically f of y1 plus h comma zeta 2 minus f of y1 comma zeta 2, and the derivative of f1 is basically d1 of f at zeta 1 comma zeta 2 times h. So from here, using this here, I'll get this is equal to k times d2 of, this is d1 of f at zeta 1 zeta 2 times h. I can take this h outside. This is kh d2 d1 of f at zeta 1 zeta 2. So this implies taking kh to the denominator of the left hand side, we'll get g y2 plus k minus g y2 upon kh is equal to d2 d1 of f at zeta 1 zeta 2. Now we know that we are given that d2 d1 exists. We were given that d2 d1 exists. We need to show that d1 d2 exists as well. Now, if you can see that gy two plus k minus gy2 gives the numerator of the equation 1. So I can directly write from equation 1. So by first, we have, we wanted to, this was d1, d2. d1, d2, f at y1, y2 is nothing but limit h comma k tending to 0 comma 0 gy2 plus k minus gy2 on kh, which is equal to, so let's notice second by first and second. This is equal to limit h comma k tending to 0 0 d2 d1 f xi1 xi2 zeta 1 zeta 2. Now we know that this zeta 1 is lying between y1 and y1 plus h, and this zeta 2 is lying between y2 and y2 plus k. Now taking h and k tending to 0, we'll get zeta 1 and zeta 2 equals to h, equal to y1 and y2. Yeah, from here, see, this zeta 2 is between y2 and y2 plus k, and from here zeta 1 is between y1 and y1 plus h. If we take h and k to 0, this is nothing but d2 d1 of f at y1 y2, which we know that exists. Since d2 d1 exists, that means this limit is finite. Therefore, we get d1 d2 exists as well, and d1 d2 of f at y1 y2 is equal to d2 d1 of f at y1 y2. Hope this is fine. All you need to be clear about is the way we define the partial derivatives. Again, this we were able to do because the partial derivatives were continuous, and hence we could apply the mean value theorem. So next we'll see one example.
Where we use the continuity.
Continuity. Yeah, continuity is used here because we are taking hk tending to 0. Explain. So yeah, in order to take this limit inside, we need the continuity of d1. So basically we had limit h comma k tending to 0 comma 0 d2 d1 f zeta 1 zeta 2. From here we got d2 d1 f at limit h comma k tending to 0 0 zeta 1 comma zeta 2. That's what we are doing. Basically, in order to take this limit inside, then only we get this zeta 1 zeta 2 to be y1 y2. So yeah, from this comes from the by continuity of d1 and d1f and d2f. So for here, yes, all the partial derivatives are continuous. Basically, we cannot take this limit inside directly. We know that zeta 1 goes to y1 if as h tends to 0, but we have f of zeta 1 comma zeta 2, and outside that we have the operator d1 as well. So for that, we need the continuity of the partial derivatives.
Only the continuity of individual partial derivative d1 and d2 are required. No?
Hmm.
The partial derivative of d2, d1.
I think partial derivative of uh, d2, d1 will also be required. So that is also given, na? That is also given to be continuous. Yes. D2, D1, F is also given to be continuous. So when everything is continuous, we are on the safe side. So let's see one example where this continuity does not hold and we get some problems. Yeah. Rest of the things, I think it's fine. Na? Everywhere we have used the mean value theorem and the definition of partial derivatives. Consider the function fxy to be. I think there is a printing mistake in those notes. Instead of xy, it should be either x or just y. Square. Then xy is non-zero. 0 when xy is 0, 0. So that the mixed partial derivatives are not equal. Uh, yeah, now try to evaluate. Firstly, d1f at 0, 0. That means, yeah, at point 0, 0, you need to use the definition. Limit h tending to 0, h comma 0 minus f and 0 comma 0 by h. And for non-zero points, you can just take the partial derivative of x square minus y square y x square plus y square. Now find these two and let me know what we're getting.
X1 means x, na? And
Yeah, x,
x2 means y.
the first variable.
X square minus y square by x square plus y square. Sorry, 3x square minus y square by x square plus y square.
So what are you getting at point 0, 0? The derivative at 0, 0.
अच्छा, so वो definition use करना होगा.
So this FH comma,
One.
one. So this is 1, and for non-zero this should be x to the power 4 plus 4x square y square minus y to the power 4 by x square plus y square whole square, and you can simplify it in any way you want. And similarly, so this d1 fxy, this is a function, something of this form. You can check that its limit, so it won't be continuous at 0 0. And xy is 0 0. So if you consider the path y equals to mx, in that case limit extending to 0, this will eventually depend on m. So this will be something of the form 1 plus 4m square minus m power 4.
XY 0 0.
0 0. 1 plus m square plus square. So which is eventually depending on m. So therefore this is not continuous. Similarly, we'll find d2. d2 means partial derivative with respect to the second variable. So in that case, you'll get it to be minus 4x by cube upon x square plus y square. Please try it yourself whenever xy is non-zero, and it will turn out to be 0 when xy is 0 0. Now you can check that. So d1 d2 f at 0 0, this is limit h tending to 0 d2f at h comma 0 minus d2f at 0 comma 0 by h. So this is d2f at h comma 0. This is uh, limit h tending to 0 minus 4. So basically this will be 0. Yeah, because y second coordinate is 0. 0 minus 0 by h. So this is 0. But the d2 d1 of f at 0 0, this is limit k tending to 0 d1 f at 0 comma k minus d1 f at 0 comma 0 by k. So from above, d1 f at 0 comma k will be minus k to the power 4 by k to the power 4. So yeah, here if you put x equals to 0 and y equals to k, from here we'll get minus k to the power 4 by k to the power 4, which is basically minus 1. So this is equal to limit k tending to 0 minus 1 minus, and d1 f at 0 0, yes, we evaluated it to be equal to 1. So this is minus 1 by k. So this is limit k tending to 0 minus 2 by k. This limit does not exist. Therefore, D1 D1 D2 is not equal to D2 D1. In fact, D2 D1 is not even well defined. So yeah, please evaluate this yourself. Yeah, if you have any doubt in today's lecture, you can ask. Also, in last class, you were asking about the definition of connectedness. Na? So, why do we not take A closure union B closure? So, basically, in order to show that two sets are separated, we use the notation that A closure intersection B should be empty, which is equal to B closure intersection A. And you were saying that instead of this, can we take A closure intersection B closure? So, yeah, for this, we have a contradicting example. If we consider the interval, open interval, A to B open interval 0 to 1 and B 1 to 2. So, in that case, obviously, these two sets are disconnected because one is not in the set. So, basically, we cannot draw a direct path from A to B. But if we take this definition, in this case, A closure intersection B closure would be close interval 0 to 1 intersection close interval 1 to 2, so this, which is 1. So in this case, we will not get this to be empty. So if we take this, so in this case, we are eventually adding some extra terms, which may be affecting the disconnectedness. That's why we take this definition.
Mhm.
Okay, if you have any
And
doubt
ma'am,
in
that in definition 11.7, definition of tangent plane to a hypersurface,
hmm,
actually I didn't get it in
the method of Lagrange multiplier.
no, definition 11.7, definition of tangent plane to a hypersurface.
11.7. I see. Tangent plane to hypersurface. Let S be subset of U. We define the tangent plane. Yeah, what is the doubt in this? So, let me explain. So if we have S is a subset of U, suppose it is a hypersurface arising at a level, arising as the level hypersurface of a C1 function, C1 smooth function f at 0. That means S is equal to f inverse 0. It contains all those points x in U such that f of x is equal to 0. We define the tangent plane at x in S. Txs is the collection of all those vectors V. It contains all those vectors V in Rn such that we can find a curve such that there exists a curve open from -1 to 1 to S such that the derivative of gamma at point 0, this will be a vector. This will be a
Yes.
linear map which will be eventually a vector in this case because the domain is a subset of R. This should be equal to V. And let me stop
Ah,
recording now firstly.
mhm. How to imagine this tangent?
That